So I'll talk about hopefully two problems. First one is the one I actually send you the note about it. So I guess this is related to so-called stochastic processes. So it's an example of that, I guess. I don't know much the theory, but as far as I understand, it's related to stochastic processes. The problem is this: suppose Alice has 7 marbles and Bob has 5 marbles. They play the following game. They toss a coin. And whoever wins gets 1 marble from the other person. Uh, the first person who gets all the 12 wins the game. Okay. So the question is, what is the average number of tossings for a game to finish? Yani ortalama kaç şeyde biter? So approximately how many times they toss the coin? Approximately, in average. Sorry, not approximately, but in average. Actually, I guess a second year student asked me. He knew the result, but he was asking about whether some probabilities exist or not, how to prove that. I came up with the following solution. So this is basically his idea to put all these numbers like this: 4, 5, 6, 7, 8, 9, 10, 11. And what we have, we may think of the same problem as follows. Suppose we have a bug or a particle at this point, and each second it moves either in this direction or in this direction 1 unit with equal probability. 50% upward or 50% downward, or clockwise and anti-clockwise, counterclockwise. And whenever the particle reaches 12, the game is over. Okay, so and then we ask the following question: what is the average lifespan of this particle, how much time it will just jump around. So we may think it this way. Think of the following problem, following experiment. I guess this is also called random walks. Okay, and it's an interesting and a difficult actually subject in involving group theory, I guess physics, several things. Each second a particle comes up from the hole 5 and it moves each second one step in either direction with equal probability. A particle that reaches 12 disappears. Okay. Now, and we would like to, use this experiment to solve the original problem. How we will do this? Well, we define the following property for any k between 1 and 12. Okay. So this is our kind of probability space, let's say omega, and we use the usual counting measure, I guess, and n equals n positive integer. This is a parameter, any integer. Let e k n, this is the probability for a particle of being at the kth place. Actually, I should say for the particle at the kth place at the end of nth second, assuming that it is released from this point 5 at time 0, assuming it is at fifth place at t equals 0. Okay, at t equals 0, it is here, and then it starts moving. Okay, it is this probability. Well then, we may just write down the following recursive relations. For example, what is E1n? At the end of the nth second, what is the probability that the particle is at the position 1? Okay. At the nth second, I want it to be here. Okay, for the particle, I want the particle to be at this point. So at the second n minus 1, it is either here or here, but if it is here, then it cannot come here because it disappears. So the only probability that at the second n minus 1, it has to be here with some probability, and with half probability, with yeah, it will go up or it will go down. So I can write this: En of 1 is just 1 half En minus 1 of 2, right? Whatever the probability for the particle to be at the point 2 at the end of n minus first second, the probability for the particle to be at the point 1 at the end of the nth second is half of that, because with 50% chance it will go upward, and 50% chance it will go downward. Okay, so I have this relation. This is 1 half E2n minus 1. What about this? Well, okay. What is the probability that the particle will be here at the end of the nth second? Well, if it is here at the end of the nth second, at the end of n minus first second, it is either here or here. So En of 2 is 1 half En minus 1, 1 plus 1 half En minus 1, 3. Okay, so I write that this is 1 half E1 n minus 1 plus 1 half E3 n minus 1, and it will go like this up to, let me say, E10. So half probability it will be here E10, E9 n minus 1, and E11 n minus 1. E11, well, to reach 11, there is only one way, because you cannot come to 11 from 12. Once you are 12, you are gone. So the only way you may reach 11 is through 10, and it is with half probability again. Çok yaşa. So this is 1 half E10 of n minus 1. And what about E12? Well, it will come either from 11 or from 1. So with half probability it will come from 1, and with half probability it will come from 11. Okay, so I have 12 probabilities, and they are parameterized with n. Okay, parameterized probabilities are called stochastic processes, as far as I understand. Now, what we do next, we write this as a matrix equation, namely, let E to be the following column vector: E1n up to En, no, E12n. Okay, then then we can write the matrix equation, namely this one: En is equal to A times En minus 1, where, what is that matrix A? A is the matrix, so you may think of this as if it's a transformation. You transform the vector n minus 1 to the vector n. Okay, from this coefficients we can write down the matrix. Let me just write down the matrix. It is a bit, it's a 12 by 12 matrix. but most of the entries are 0, so I can describe you 0, and then I have 1/2, and then I have zeros, and then I have 1/2 here, 0 here, 1/2 here, and then again zeros, and here it will go like this, and the last one is 1/2, and then 0, 0, and it will so this column is all 0 because 12 doesn't go anywhere. Okay, so it is not a non-singular matrix, and the column before this, it goes like this. I have 1/2 here, 0 here, sorry, 1/2 here, and we have this gadget here. So diagonal entries are all 0. Above the diagonal I have 1/2s, and below the diagonals I have 1/2s, but I have also an extra 1/2 here. Okay, so we have this gadget, and I have also the following information. What is E0? The probability of the particle to be at the first place. It is 0 because it is at 5. So this is 0, 0, 0, 0, and then 1 because it is at the point 5 at time 0, and then again all zeros. Okay, so by multiplying our initial vector, so En is just what? A times En minus 1, but this is a squared En minus 2 because En minus 1 is, okay, let me write it this way, a times En minus 2. So this is a squared En minus 2, and I can continue up to 0. So this is e to the power n E0. So if I can calculate nth power of this and multiply with this, I will get all the probabilities. Okay. Uh, of course, you know, it's not an easy task to multiply the matrix n times, but there is the following fact. Maybe computing the nth power is not easy, but computing all of them and adding them up is easy. What I mean is the following. Let me write the conclusion here. So for the particle who comes up at t equals 0, comes up uh, uh, from 5 at t equals 0, its probability for being at the kth place at the end of the nth second is EKN. Okay, where EKN, where En is no, En is a to the power n times E0. Okay, and EK is the nth entry of this column matrix, column vector. In particular, in particular the average number of particles at the kth place at the end of the and second is the summation is the sum sorry the particle for the particle who comes up at t equals 0 to be at the kth place at the end of the nth second is a k n. For the particle who comes up at the first second to be at the kth place at the end of the nth second is a k n minus 1, and it will go like this. Yes. So this is the particle who comes up at the 0th second. The next one is the particle who comes up at the first second, and this is the particle who comes up at the nth second. Doğru mu yaptım? Yok. Bu sıfırıncı saniyede yukarı çıkanın k saniye sonra nereye gittiğini gösteriyor. Pardon, n saniye sonra. Karıştırdım. Evet. Evet. Yeah. This is the probability for a particle to be at the kth place at the end of 0th second, and then the probability for a particle to be at the kth place at the end of first second, and so on. So this total sum is the number of particles, or yeah, the average number of particles at the position k at the end of the nth second. Okay. If you take time to infinity, you will get the limiting number of particles at the end of at the kth place, right? Hence, the limiting number of particles at the kth place is I from 0 to infinity. So it is this one. Okay. And this is nothing but just AI I from 0 to infinity times E0 and the kth entry of that column vector. Okay. So I am just summing EK0, EK1, EK2, EK3 up to infinity. Okay. That's the limiting number of particles. Well, this is of course just this sum times the vector E0, and then you take its kth entry. However, we can compute this. This matrix, the matrix A has norm, matrix norm uh, less than 1. You can just use, for example, the norm, uh, sum the squares of the entries and divide it by, for example, n. You can use that norm. Yani entry'lerin karelerini alıp toplarsanız 1 bölü 2'den küçük oluyor. Pardon, 1'den küçük oluyor. Yani hepsini toplayıp n'e böleceksiniz. Öyle bir norm tarif ederseniz. O zaman this matrix has norm less than 1 and this implies n kare olabilir. Ya da bilmiyorum. Şimdi bir kalımın normu direkt karelerini alıp topluyoruz. N'e bölmüyoruz. Yani ikisi de olabilir herhalde de. Yani birden fazla şekilde tarif edilebilir. Buradaki kritik şey şu. And thus this series is convergent. So when you take the powers and add them up, you just sum up the entries of powers, and those numbers are those sequences will be series will be convergent. So this is convergent and equals şey gibi düşünün. This is geometric series, so it's equal to 1 over 1 minus a. Okay. Well, of course, in matrix notation, this is just identity minus a inverse. Okay. And you can compute it. I used online matrix, calculators. All we need is just the actually fifth column of this, and the fifth column is this, because I will multiply this by 0, 0, 0, 0, 1. So I need the fifth column of this, and the entries are like this. Oops, pardon. 7 over 6, 7 over 3, 7 over 2, 14 over 3, 35 over 6, 5, 25 over 6, 10 over 3, 5 over 2, 5 over 3, 5 over 6, and 1. Okay. So this is the fifth row, fifth column, sorry. Hence, E infinity, let me say, E infinity, the limiting probability. So this is just I from 0 to infinity is 0, which is identity minus A inverse times E0. It is just, of course, the fifth column, the fifth column of what? Identity minus A inverse. So what is this? Of course, E infinity is the following. E1 infinity, and so on up to E12 infinity, right? These are the number of particles at each place as t goes to infinity. Okay, they reach a equilibrium value, and these are the values. So the total number of particles on the experiment table is what? Just the sum of these, right? Because at the first place we have that much, and second place, and so on. And if you just sum up these numbers, you just get 35. So it means as t goes to infinity, the number of particles on the experiment table becomes approximately 35. Well, each second, one particle comes up and it goes around for a while and then it disappears. But on the average, we have 35 particles on the table. It means each particle has a lifespan of 35 seconds, right? Approximately. It stays around 35 seconds so that the number on the table becomes, stationary at 35. Hence, the average lifespan of a particle is 35 seconds. So it means each second corresponds to one tossing in the first experiment. So the game Alice and Bob are playing will approximately last 35 tossings. Okay. Hence, thus the game Alice and Bob are playing will end approximately at the end of the 35th tossing. Okay. Yok, E infinity'yi böyle şey yaptım. Aslında belki buna E infinity dememek lazım. Total çünkü bu sayı değil mi? Şöyle diyeyim. E infinity, şöyle bir total koyayım. Total number. Yani kastettiğim şey bu toplam. Tamam mı? O işte bu. Yok, incik kalımı değil. Bunlar kalım değil. K'ıncı noktadaki particle şu mu? Tamam. Zamanı sonsuza götürüyorum. K'ıncı place'teyim. Zamanı sonsuza getiriyorum. Bu Tamam. What I mean by this, this is a matrix. I multiply with this column vector. I get a column vector. I mean it's kth entry. Yeah, kth entry. Uh, so this is just the kth entry of the column. Which column? This one. Efendim? Yok ama hani biraz şey bir notasyon bu. Alışık olduğumuz bir notasyon değil. Tamam mı? Bir tane de distribution'larla ilgili örnek yapacaktım ama zamanımız kalmadı. Aa, onu da olmazsa yazar notlara koyarım. Okay. Do you have any questions? Once we are over with finals and so on, I will continue to record videos for the course uh, because we covered, I guess, like half of the book probably. So I want to cover all of them. I'll put the videos to YouTube, so you may, if you want, you may watch them. I will put my lecture notes also. I will post them in my web page, so you may uh, study. Okay, let me stop here.